Okay, hi everyone. Thank you for joining us today. We have Betsy Stovall here from Madison who will tell us about how the Fourier restriction to the sphere is extremizable more often than not. Thank you.
Good morning, everyone. I hope you're all doing well wherever you are. I want to start by thanking the organizers for the invitation to speak here. It's a time when there are a lot of distractions that are non-mathematical, and it's really nice to have a deadline sometimes. So the work I'll be describing today is joint with Taryn Flock, who's at McAllister, and we'll discuss Fourier restriction to the sphere and extremizers thereof. So I just want to start by, this will be a talk in the area of sharp Fourier restriction theory. And the general idea is that we suppose that we have an inequality. So I have a function, I have a class of functions f. They live on some manifold sigma in Rd. I have a measure, d sigma, on sigma. And I want to know when f d sigma hat in Q is bounded by some universal constant times the norm of f in LP. And once one knows and it has an inequality like this, one can ask a number of questions. So the first is, what is the optimal constant C? That optimal constant, of course, is the operator norm of this extension operator that sends f to the Fourier transform of f sigma. That question is often very hard. And so one can instead ask the following, whether there exist non-zero functions f for which equality holds. When C is equal to C opt. So this question is, the answer to this question can sometimes be yes, it can sometimes be no. And so it's interesting to determine whether these things exist. And it's often easier than asking what is the optimal constant. Now, a little bit harder than either of these questions, and an extension of these is asking who are these functions f that realize this constant. So other questions one can ask related to this first is, do extremizing sequences that is, sequences that saturate the operator norm can have subsequences that converge modular symmetries. And a little bit more generally, what properties do extremizers have? One can also ask for properties of near extremizers. So those are functions that miss the optimal constant by just a little bit. By quasi-extremizers, those are functions that are bounded below by something that's smaller than C, but not too small. And also epsilon quasi-extremizers, where this constant might be very, very small. So today we'll focus on these questions in the case of the Fourier restriction and extension operators for the sphere. And so here we have, just to fix the notation, we have sigma equal to the D sphere in RD plus 1, and d sigma is the natural surface measure. And the conjecture is that the norm of f d sigma Fourier transform in LQ of R d plus 1 is less than the norm of f in LP of S d sigma. This we're going to call the extension of f for every P and Q with Q greater than 2 d plus 1 over d and Q greater than or equal to d plus 2 over d p prime. So the current records for this, so this is open in all dimensions greater than or for d greater than or equal to 2. It's solved for d equal to 1, and the records in higher dimensions are due to Guth, Wang, and some subset of Hickman, Rogers, Zoll, depending on the dimension. So these results are all stated off the scaling line. And I want to highlight that for results on the scaling line, the bilinear theory is still useful. And in the talk today, there will be the scaling line will be a little bit special. So now let's turn to the questions of sharp Fourier restriction estimates on this surface. So two results that are particularly relevant to our discussion today in 2011, Finelli, Visiglia, Vega. Okay, there are a lot of Fs as authors in this business, and so I'm going to apologize for using, so maybe I'll use F at the first two letters as initials. So Finelli, Visiglia, and Vega. And I always put those in the wrong order, sorry. So extremizers exist. When P is equal to 2 and Q is larger than 2d plus 2 over d. And in 2016, Franck, Lieb, and Sabin proved that for P equal to 2 and Q equal to 2d plus 2 over d, non-concentrated, so either extremizers exist or extremizing sequences converge within Thibodeau symmetry. So concentrated symmetrically at antipodal points. So the reason that I want to highlight these results, they have a couple of things in common with the result that we'll discuss today. So the first is that the dimensions are arbitrary. And aside from these sort of basic scaling and subcritical conditions, there aren't any other special arithmetic properties of the exponent q. But there's a pretty strong assumption on P, and our goal is removing this assumption on P. So the reason these results are able to be as general as they are is they utilize profile decompositions. Unfortunately, the theory right now for profile decompositions is best developed when P is equal to 2 and not for other values of P for reasons that I'll discuss in a moment. Other results. And so one can ask, if one knows that extremizers exist, one can also ask who they are. The best guess is constants, but that's known in only a few cases. And so I'll mention some cases where this is known. So Christ and Shao proved in 2012 that when dpq is equal to 2, 2, 4, extremizers exist and are smooth. And Fourier in 2015 showed that they're constants. So we know in some cases that the extremizers are constants. And in fact, in every case where we know what the extremizers are, they are constants. So there are a number of other results, and it will take too long to go through them in detail, but I do want to mention, so there are results of Carneiro, Oliveira, e Silva, Guilherme, and Sousa. Showing that under various arithmetic conditions on P and Q, extremizers exist and are constant. So all of these results very strongly use the fact that, so it's pretty typical that Q might be an even integer in these estimates. And the reason that's important is that allows one to recast the extension inequality as an inequality for a convolution operator, and allows one to get a better handle on what's going on with this operator. There's also a recent result of Gonçalves Negro in 2020, which showed that constants are local maximizers when P is 2 and the dimension is up to 60. This is for the Stein-Thomas inequality. Okay, so now I'll state our results. And we will assume the extension conjecture. It makes results easier to state. However, it's enough in proving our results that the extension conjecture holds on a neighborhood of the point under consideration. And I'll draw you a picture in just a minute to explain what that means on the scaling line. So, but for the most part, we're going to assume. So I'm going to draw a picture. Here's 1 over Q. Here's 1 over P. It's 1, 1. And here's the line P equals Q. And so I think 1/2 is about here. And so our estimates are a little bit below. So the assumption is that in this trapezoidal region, we have the boundedness of the extension operator. In reality, we need less than this. So for points here, we need validity of the conjecture in the neighborhood of the point. And for points on the scaling line, again, we need validity of the conjecture in a neighborhood of the point where we already know the conjecture above the scaling line because it's false. The inequality is false. So our theorem so let's let Q greater than P greater than 1 with Q greater than or equal to D plus 2 over D P prime. Then non-concentrating. Extremizing sequences. Possess subsequences that converge after modulation. Non-concentrating bounded. Have subsequences that converge modulo modulations. In LP to an extremizer. So this is complemented by the following proposition, which is a very easy consequence of Hölder's inequality. And it states that when Q is off of the scaling line, extremizing sequences cannot concentrate. And so, as a corollary, extremizers exist in the open blue region. Drawn here. And so if you look at the picture, this is the sense in which these things are extremizable more often than not, because this blue triangle is bigger than half of the whole trapezoid. So I want to mention there's some past work that's related and in particular is connected with existence of extremizers for a large number of LP-LQ inequalities. So I have a result that's the case of the paraboloid. And Chandan Biswas and I prove that extremizers exist in the case of the movement curve. And it's the analogous result except along the scaling line. So what's new in the talk today, and I'll try to highlight these differences, is the following. So the first thing is that the symmetries are broken. In particular, the dilations that exist for both the sphere and the paraboloid are no longer with us. This complication was already addressed by Franck-Lieb-Sabin. In the case of when p equals 2 for the sphere. And the other thing that's new is that the sphere has finite measure, and therefore there are strictly local inequalities, and there's an open region of p's and q's on which the inequalities can hold, and that gives us a bit more flexibility and a richer family of inequalities. Now, this was already used in a very strong way in the work of Finelli, Vega, Visiglia. Again, when p is equal to 2. Now, we're addressing the case when p is not equal to 2. And what we add here is a profile decomposition for non-concentrating sequences. And because L2 is not a Hilbert space, this turns out to be a little bit more subtle. I mean, for LP, when p is not 2, is not a Hilbert space, and this turns out to be a little bit more subtle for reasons I'll explain. Okay. So now I'll give an outline of the proof. And the first step is a frequency scale decomposition. For non-negligible sequences. And so here's the theorem. So for 1 less than p less than q, and q greater equal d plus 2 over d p prime, if fn in LP is bounded, then there exist a few things. So a subsequence. I'm just going to use the same notation for subsequences. There exists a sequence of scales, lambda in J. These are in 0, 1. And these have the further property that they're either identically 1 or they tend to 0. So this is the case of non-concentration. This is the case of concentration. Now, next, the concentration happens around antipodal points. So we characterize antipodal points. We think of these as a line. And finally, decompositions. Fn is the sum from j equals 1 to j. Fn, j, plus the remainder. such that. So first of all, we have really good LP orthogonality. These are actually, the supports are pairwise disjoint, and so we get the following. So for n and j, the norm of Fn in LP is just equal to the sum of the Fnj, LP to the p, plus the sum of the remainders. Secondly, we have very good LQ orthogonality if we let n go to infinity. So the extension of Fn in LQ to the q minus the norms of the extensions of the Fnj's in LQ to the q minus the extensions of the Rnj's in LQ to the q, that's equal to 0. Now, thirdly, the remainder terms are small. Okay, and now I just want to note that so far I haven't told you much of anything. So I could take Fn1 to be equal to Fn, and all of these conditions would be satisfied. What gives this statement the meaning is the following. The limit as m goes to infinity, the lim sup as n goes to infinity of the norm of the extension of f in j. So this is the sense in which, so somehow the idea is that f in j is well adapted to a lambda in j neighborhood of omega in j, this pair of antipodal points. So this times the characteristic function of the set where the distance from omega to omega in j is bigger than, is much larger than lambda in j, or f in j is really large. This limit is equal to 0. So the contribution of Fn is really, this is the sense in which Fn is really concentrating around this antipodal point. I just want to point out, so again, by an elementary application of Hölder's inequality, j is equal to 1, and Fn1 equals Fn obeys 4 when q is larger than d plus 2 over dp prime. And so a particular observation is that in the extremizing case, because q is larger than p, and we have here Fn decomposes as orthogonal parts in LP, and the extension decomposes as orthogonal parts in LQ, and Q is larger than P, there can't be too many of these profiles. And in fact, if we're extremizing, there's only one frequency scale. So the proof of this is elementary. In the case that Q is larger than D plus 2 over D, P prime, I'm going to give you an idea of what goes into the proof when when P and Q are on the scaling line. Okay, and so the key lemma is that it's an improved version of the restriction inequality. And so it states that for F in LP, the norm of the extension of F in LQ is less than. So normally I would just have the norm of F in LP over here. What I'm going to do instead is I'm going to take the sup on tau of the size tau to the minus 1 over P, the norm of the extension of F in L infinite F tau. So F tau, this is F times the characteristic function of tau, P, this to the theta, this to the 1 minus theta, where tau is the cap. So in order to prove the lemma, this follows what is by now a well-established route of using the bilinear restriction and the bilinear to linear argument and keeping a little bit closer track of what one really needs to close that argument and sort of saving the extra terms. Now, this lemma gives us what we think of as a sort of a chip decomposition. So I think, so these taus, these caps tau, I think of as chips. And I'm going to chip off little pieces of my sequence until I'm left with something that doesn't have much of an extension. And what a chip off is suggested by exactly picking out what maximizes this inequality. And so the proposition is that we're going to write Fn as the sum of some Fnj's plus some remainders. Here the Fnj's are pretty well adapted to a chip. So we make this as an iterative procedure, and so given a remainder, with our chip, we're going to take the chip Rnj minus 1 times the characteristic function of our cap times the characteristic function of the set where F is not too big. Not too big becomes a weaker and weaker condition as we go further in this decomposition. So once we write this decomposition, then the conclusion is that the limit as j goes to infinity, the lim sup as n goes to infinity of the norm of the extension is equal to 0. So this has a lot going for it in terms of what we wanted in the previous theorem. So we have that the errors are small here. By construction, we have that the supports of all these pieces are going to be pairwise disjoint. And so we have good LP orthogonality. What's bad about this is that we don't have LQ orthogonality of the extensions. Okay, and so in order to regain that LQ orthogonality, what we're going to do is we're going to reorganize those chips into chunks. And so what we say is that tau in J and tau n j prime are in the same chunk. If their sizes are comparable. This limit is in 0, infinity. It's not 0 and it's not infinite. And the limit as n goes to infinity of the distance between the two chips divided by the size of the chips converges. So now we group together the chips that are in the same chunks, and those give us a new decomposition. Okay, so to be super pedantic, this isn't quite, this is kind of a redundant sum, but obviously you take out the redundant terms here. So we still have that the supports of these are disjoint, but now we gain LQ orthogonality, and the way that we prove that is by either an easy Hilder's inequality using the fact that using this bound here on the size of f on these chips, or by linear restriction. You can sort of see where bilinear restriction would come in if we look at this condition. So in bilinear restriction, normally we have two chips whose distance is comparable to their length. In this case, we have two chips whose distance is much larger than the side length, and so that gives us an improved inequality and low interaction between those terms. So the second step is a spatial decomposition of the scale 1 pieces. And so we have theorem 3. So let's let 1 less than p less than q less than infinity, and q greater than or equal to d plus 2 over d p prime. And let's say that we have a sequence Fn in LP. It's bounded. We're going to assume a bit more. We assume that the limit as n goes to infinity, so we're only in the non-concentrating case, the lim sup, as n goes to infinity, the norm of the extension of Fn times the characteristic function of the set where Fn is bigger than n, and LQ is 0. So this is our hypothesis. And under this assumption, so after passing to a subsequence, we have a decomposition. So Fn is the sum from j equals 1 up to j of e to the I x in j dotted with omega phi j plus some remainder term. Where, first of all, the phi j is a weak limit. And this is for all j in n. And so, of course, as j goes to infinity, we should get a better and better decomposition. So phi j is the weak limit of e to the minus I x n j omega fn. Secondly, the limit as n goes to infinity, we have good LQ decoupling, Fn. I shouldn't say decoupling, but good LQ orthogonality, and LQ to the cube minus j equals 1 to j, the extension of phi j, and LQ to the cube minus the extension of Rn j, and LQ to the cube is equal to 0 for all j and n. Thirdly, we have kind of okay LP orthogonality. It'll be good enough to make the theorem work, but it's not as good as what happens in L2, and I'll explain what happens in L2 in a moment. So we have two inequalities. So the first is that the sum on J of the norm of phi J in LP to the P twiddle, 1 over P twiddle. Here, P twiddle is the max of P and P prime. This is less than or equal to, and it's very important here that this is less than or equal to and not less than the limit of the norm of Fn in LP. Secondly, we can look at sort of the adjoint version of this inequality, which states that when I put these pieces back together, this is bounded by the norm of the phi j in LP to the P twiddle prime to the 1 over P twiddle prime. So I want to contrast this to the case when P is equal to 2. When P is equal to 2, we have a much stronger condition, which is that the limit as n goes to infinity of the norm of Fn in L2 squared minus the norm of the phi j's in L2 squared minus the norm of the remainders. These are completely orthogonal and as in the limit, and this is equal to 0. Now this condition is the condition we've written down is rather weaker, and in particular, the condition we have is not strong enough to control the LP norm of the remainders. This doesn't rule out the possibility that the remainders have LP norms that blow up in the general case. However, in the range when Q is larger than P, Q is still larger than P twiddle, and so this will allow us to prove our result on extremizers. And finally, of course, the fourth condition is that the extensions of the error terms are small. And so as a corollary, we obtain the result about the existence of extremizers. So Q greater than P twiddle allows us to show, oh, there's only one profile. And that LP convergence holds. What's new in this result is that we have, especially relative to the case of the sphere or the moment curve, is that we actually have a full profile decomposition here instead of just dealing with the case of extremizers. Oh, and I should have mentioned, so the case when P equals 2, that's not a new result in this article. That was the case P equals 2 of this theorem was essentially known before. It might not be stated exactly this way, but from the work of Frank Lieb-Savin, Finelli, Vega Vistiglia. So I'll close with a sketch of the proof of this theorem. And so let's deal first with the case that the FNs are bounded. So in this case, my sequence is bounded in L2. And because it's bounded in L2, I can use the L2 profile decomposition. And we have two important conclusions in this case. So first of all, we have this separation condition. In LQ2, so Q2 is equal to the scaling exponent corresponding to 2. So this minus so this goes to 0 for all j. And we have, secondly, that the norm of the extensions of the remainders goes to 0 in the way we expect. Now, this is much easier to prove when when P is equal to 2, and that's because we have this sharp orthogonality here. So every time we have a non-negligible limit of our remainder terms, we can find a non-zero weak limit. We subtract that non-zero weak limit, and we make not only do we make the LQ norm smaller by this inequality, but we actually also make the L2 norm smaller as well. And we iterate that process and eventually get to 0 remainder, or at least 0 extension of the remainder. Now, when P is not equal to 2, one still holds. So of course, when P is not equal to 2, this decomposition is also immediately going to give us a decomposition in LP. We just want to make sure that it has the properties that we want. So the condition 1 still holds. Okay, so 1 with Q not equal to Q2. And it's it's proved along standard lines using Gréchy's Lieb. So what it allows us to do is it allows us to control the extension of the remainders in a bunch of spaces. And so in particular, what we're going to do, we have our diagram here of where our inequalities fold. And we have our point PQ that we're interested in, and we're going to pick this point here at, this is 2d plus 2 over d. And here's the point we're interested in, and we just pick a point on another side of it. And using the estimates at these points, we get that via Hilder. Implies that 2 holds with Q not equal to Q2. So we can erase the subscript 2. Oh, sorry, this is the subscript. So with Q2, could be replaced by Q. And so the LP orthogonality result follows by bounding a certain vector valued operator a la Talvargas and Vega. The only difference is we need the norm to be 1. And that uses Fourier decay of the extension of 1. So case 2 is I want to remove this hypothesis. So Fn is bounded in LP, but no other bounds, so no pointwise bounds in particular. What I know now, so I have a sequence, so I can look at the Fn m's, which is Fn times the characteristic function of the set where Fn is less than or equal to n. And the idea is that these guys should be picking up most of the extension in a quantitative way, in a way that's uniform in n as n goes to infinity. And so then I can apply the previous result, and I have a bunch of decompositions. Fn m equals e to the I x n j m dotted with omega phi j m plus remainders. And what I want to do is erase the superscripts m. And so, of course, the obstruction here is that I have no a priori way of just looking at this and seeing that as n goes to infinity, these pieces are going to converge in any meaningful sense to some fixed decomposition. So the first lemma is that the extensions of the remainders go to 0 in a way that's quantitative and uniform in n. So given some epsilon greater than 0, there exists a j epsilon, that's how far I have to go out in the remainders, and an m epsilon, such that the norm of the extension of the remainders LQ is less than epsilon for every j greater than j epsilon and m greater than m epsilon. And so the idea of the proof is to use the fact that Q is larger than P tilde, plus the and some convexity arguments. And then the second lemma is that lemma 1 continues to hold, but I can replace the x in j m's, I can erase the m's. So I want to give an idea of the proof of lemma 2, and that will be the end of the argument. So I'm going to say that x in j m and x in j prime m prime are in the same lump or pile if the difference converges. As n goes to infinity, and they're different piles otherwise. So along any pile, the weak limit of e to the minus I x in j f n, there's no, notice that there's no n here because anytime I have a pile, I can pick one representative. This has a non-negligible extension. However, if they're distinct piles, they have good LQ orthogonality. And so that means, taken together, many distinct piles, if there are many distinct piles, then the extension of Fn in LQ is too big. And so then once I control the number of piles, I can let m go to infinity. And I will stop there. There are a number of open questions here, so two that I want to mention are who are the extremizers, or what are their properties? And secondly, what happens when Q is less than or equal to P? With our techniques, one needs to know a bit more about the extremizers before one could apply our results to obtain any information about the case Q less than P. And we're very strongly using convexity arguments in following this approach directly. There's interesting recent work of Stefan Buschenhenke, though, that is, it's a slightly different setup, but it's related to this case when of the near extremizers when Q is less than or equal to P. And I'll stop there. Thanks.
Thank you very much. So let's all unmute ourselves and thank Betsy for a very interesting talk. Thank you.